Okay, great. Thanks so much, Christian, and thanks for the invitation. It's nice to be here and see what life is like in East Lansing, even in the cold months. You know, it's best to see what a place is like in all months. You shouldn't always visit a place in its optimum situation. So I'm happy to be here also at this time, even during Thanksgiving week. So thanks everyone for joining today. So yeah, as Christian mentioned, I'm going to be introducing some equations of state that I've worked on during my time as a PhD student. And let's go ahead and get started. So first of all, there are still many open questions about what is the phase structure of QCD, namely whether there's a critical point in the phase diagram, which would demarcate the end of the crossover phase transition that we know exists at low values of the density or the baryon chemical potential, and would begin a new type of phase transition, the first order phase transition. So this has been a very active area of research in my field, which is more toward the heavy ion collision phenomenology. But in addition, it's also been another topic of my dissertation to characterize the transition at low density. So what are the different degrees of freedom in the vicinity of the phase transition? And in addition, can we draw the full transition line out to high density? What does it look like? Where does it terminate on the UV axis at t equals 0? And in addition, what are the exotic phases that are created at high density in strongly interacting matter? So some heavy ion collision experiments can actually help answer this question. Sorry, did I hear a question or? Okay, I'll continue. So this phase diagram that I'm showing over here on the right in terms of temperature and the net baryon density also shows several different experiments for both the heavy ion collision, different facilities, including the facility here in the US, the Relativistic Heavy Ion Collider, and in addition, the SPS at CERN, and some future facilities that will be coming online, hopefully in the next few years. FAIR is actually left off of this particular phase diagram. Oh, no, here's FAIR down in the higher density region. So as we get more data from those heavy ion collision experiments, we can start to map out this phase diagram. And one reason that I chose this particular phase diagram is because there's also, beyond information about heavy ion collisions, some information about what happens when you have a non-symmetric nuclear matter. So there's some difference between the proton and neutron number, and we can draw actually sort of a three-dimensional phase diagram and see where neutron-star mergers and things of that nature actually live in the QCD phase diagram in extra dimensions. So as far as heavy ion collisions go, there has been a lot of efforts for the search for a critical point in the phase diagram of QCD, specifically with the beam energy scan program at RHIC that actually just completed its runs earlier this year. So part of the search for that critical point is determining which experimental observables are actually likely to carry signatures of the critical region. So if the behavior of some observables starts to change as a function of the beam energy, then this could possibly indicate the termination of this crossover type of phase transition at low baryon density. So some non-monoticity in the behavior of a specific quantity, like I'm showing, for example, here for a fourth order moment like the cortosis. If you see some peak and then perhaps also a dip at the different baryon densities or beam energies, then this could indicate the presence of a critical point. So this fourth order moment actually presents one of the best candidates to determine the location of the critical point from heavy ion experiments, and understanding the effects of a critical point on the observables in heavy ion collisions is something that we need to do as we begin to interpret this beam energy scan data. So to complicate matters even further, this phase diagram that we all know and love, as I alluded to on the first slide, is not a two-dimensional phase diagram, but there are further axes that we should be considered whenever we're modeling strongly interacting matter, particularly for this talk for heavy ion collisions. So one additional question is, what is the phase structure of QCD when we go beyond this two-dimensional phase diagram into a fully four-dimensional hyperplane that considers not only the baryon chemical potential, but the chemical potentials of the other conserved charges, like the strangeness chemical potential and the electric charge chemical potential? Because the equation of state, the partition function for QCD, of course, depends not only on mu b, but also on mu s and mu q. So a big question is, what is the behavior of the heavy ion collision matter, of this strongly interacting matter in heavy ion collisions in this slice that the heavy ion collision trajectories follow of this 4D hyperplane phase diagram of QCD. So the equation of state is available for different observables, specifically for the equation of state, specifically for different conditions on the conserved charges. So the lattice data is available at vanishing, strangeness, and electric charge chemical potentials, but it's also available in what's known as the strangeness neutral trajectory, which is this slice of the phase diagram that heavy ion collisions will follow based on the initial conditions that come from the colliding nuclei in these experiments. So namely, we have global net strangeness density. So you start with just protons and neutrons, therefore there's no strangeness in the beginning in the system. And in addition, there's a fixed ratio of electric charge to baryon number of about 40% in these heavy nuclei, such as gold and lead. So what I'm showing in the plots here are the different Taylor expansion coefficients for the pressure in the case of this strangeness neutral equation of state. And on each of these curves, the lattice data is from the Wuppertal-Budapest collaboration is shown, but this has also been prepared calculated by the HIC QCD collaboration as well. But what I want to emphasize on these plots is what you see in the low temperature regime, which is this red curve here, which is the Hadron resonance gas model calculations, which agree well with the lattice data in this hadronic regime, so this low temperature regime. And that's going to be one tool that I will use throughout this talk. So as I said, it agrees well with the equation of state, but maybe first I should introduce what the equation of state is, what all observables make up the equation of state. So over here on the left, I'm showing a few different variables for the equation of state as calculated by the HIC QCD collaboration. So in red, we have the pressure and its agreement with the HRG model as the red curve as well, in addition to the entropy shown in green and the energy density shown in blue. So these are all calculated from, or these can all be calculated, these variables for the equation of state from the partition function of QCD, of which you can get the pressure, and further derivatives of the pressure will give rise to the other quantities making up the equation of state. In addition, the Hadron resonance gas model has also been shown to agree well with further lattice QCD quantities, such as the susceptibilities or the fluctuations of conserved charges, which are basically the derivatives of the pressure with respect to the different conserved charge chemical potentials. So in addition to the equation of state, more differential quantities like these susceptibilities also agree well with the lattice QCD data. So, but what actually is the Hadron resonance gas model? So this is a statistical treatment of the hadronic phase, where we actually are using the grand canonical ensemble in this case to write our partition function. And this treats the system of hadrons as a non-interacting system of hadrons and resonances. So in order to model the attractive interactions between the different hadrons, we can actually treat it as a non-interacting system of hadrons and their higher lying states. So one important feature of this model is that we can actually transform this momentum integral into the one that's appropriate for experimental conditions in order to apply the cuts in transverse momentum and rapidity. Okay, so I'll utilize the Hadron resonance gas model in this talk, but first I want to go through, because as far as I understand, this is a somewhat broad audience in here at the talk today. So I want to go through what are the different stages of a heavy ion collision and how the equation of state can play a role. So first of all, these are relativistic heavy ion collisions. So when the incoming nuclei actually collide, they're very Lorentz contracted, and they can, they basically are little pancakes or so that collide along the direction of the beamline. And after some formation time, the energy is deposited into the system such that actually the quarks and gluons can become deconfined and form the quark-gluon plasma phase. And after this, initial energy is deposited into the system, we can begin to describe the system with hydrodynamic equations. So this is the point where we need the input for the equation of state of the system in order to be able to actually run those simulations of heavy ion collisions. And after some time, actually the system has to cool and has to go back into color neutral states. And once it does so, this is the stage called hadronization. We form hadrons again, and then with further cooling, and as the system spreads out again, it goes through 2 freeze-out stages. The first of which is the chemical freeze-out stage, where essentially all inelastic collisions cease. So you can no longer form different types of particles, and at that moment, the chemistry of the system is fixed. So the particle yields and the fluctuations are fixed at this stage. And with further cooling, we finally have such a sparse system that the particles can actually no longer collide elastically. And so this is known as kinetic freeze-out. And after these freeze-out stages, the particles are free to fly into the detectors to be measured and analyzed. So the first equation of state that I want to present here today is one that is fully 4-dimensional, so taking into account the dependence on T, mu B, mu S, and mu Q, so all the conserved charge chemical potentials in QCD. So we were able to do this by utilizing the susceptibilities from Lattice QCD that I introduced just before, and reconstruct the Taylor expansion of the pressure from those basically Taylor coefficients, where we can utilize the susceptibilities as calculated on the lattice in order to do the expansion in mu B, mu Q, and mu S. So these were 22 different coefficients that needed to be utilized in order to reconstruct the pressure in the QCD 4-dimensional phase diagram, but they're only available in a limited temperature range. So we need to fill in some information as a function of temperature in order to be able to have enough of the coverage of the phase diagram for these hydrodynamic equations. So in order to do so, we utilize the Hadron resonance gas model in the low temperature regime, where we know the system is in the hadronic phase, and also imposed an approach to the Stefan-Boltzmann limit at high temperature. So we parametrized each of these susceptibilities via one of the 2 equations here. So for most observables, we could fit it with this ratio of higher order polynomials, which is essentially like a Pade approximation. But for the Chi2b, we actually took this parameterization from the literature. It was shown that this is a nice fit for this particular susceptibility. So in this case, we chose to go ahead with this parameterization. So the plots I'm showing here are just examples of 4 out of the 22 different susceptibilities. So what you can see is for each of the susceptibilities in the low temperature regime, we have the Hadron resonance gas model calculations as merged with the Lattice QCD data in the moderate temperature regime. And then we impose a smooth approach to the Stefan-Boltzmann limit at high temperature. So this is just a few examples of our parameterizations of each of those quantities. So after that, we're able to actually reconstruct the Taylor expansion of the pressure And this is a few examples of the quantities that make up the equation of state, including the pressure, which you can see is a nice smooth function of T and UV up to a very high temperature and moderate chemical potentials. So if I were to estimate my chemical potential range in terms of density, this would be roughly half the nuclear saturation density or so. It's going up to 450 in MUV, so that's quite low for those interested in neutron-star mergers. But this is still based on a lattice result, and therefore our Taylor expansion is limited at this stage. But if we can go beyond some lattice information, maybe we can figure out how to extend the coverage in the phase diagram. So I'm also showing the baryon density as well as the energy density here, which you can see our coverage of the phase diagram for those observables. So we made sure that our construction in terms of implementing these conditions on the conserved charges that are relevant for heavy ion collisions are actually achieved within our results. So for the different quantities that make up the equation of state, we looked at what does the pressure look like for vanishing values of μs and μq versus the strangeness neutrality conditions. And you can see for the thermodynamic quantities like the pressure, the entropy, and the energy density, they're only affected at the higher temperature regimes. But of course, the densities reveal actually the effects of applying these conditions on the conserved charges. Namely, now we can ensure that the global strangeness density is indeed zero, whereas before, when the strangeness chemical potential was fixed to be zero, the strangeness density was actually becoming finite in order to keep the conditions such that the strangeness chemical potential would be zero as well. And so you can see that we have the correct description of a system for heavy ion collisions in the case of applying these constraints on the densities. So furthermore, what we could do is actually see how the paths through the phase diagram for a heavy ion collision are affected whenever we utilize these two different sets of conditions on the conserved charges. So in this plot, I'm showing the so-called isentropic trajectories, which correspond to a fixed entropy per baryon number, where in the absence of dissipation, this is essentially the path of the heavy ion collision system through the phase diagram. So the red dotted line is the one for vanishing chemical potentials, and the gray solid line is for strangeness neutrality. And what we can see from these different curves for different beam energies is that they have vastly different initial conditions that they actually would exhibit in the phase diagram. So this stresses furthermore that we need to have the correct constraints on the conserved charges in order to model heavy ion collisions. Okay, so the next equation of state that I have worked on during my doctoral studies is one that incorporates some extra features beyond those from Lattice QCD, including a critical point. So we can study the effect on the heavy ion collision observables by actually preparing the equation of state that includes this critical point that can be used for hydrodynamic simulations and to study the effect on the observables in heavy ion collisions. So this equation of state is actually an already existing equation of state before I got involved as a PhD student. And this was created within the framework of the BEST collaboration. And this specific equation of state utilizes some universality class arguments, which I'll go into detail. But the one that I've worked on in my PhD is to implement these conditions on the conserved charges such that it is actually consistent with the heavy ion collision picture. So in other words, implementing these strangeness neutrality conditions. So this new version, as I said, has the conditions of strangeness neutrality, but we also implemented a different type of treatment of the hadronic states in our equation of state, such that one could couple these hydrodynamic equations that utilize this equation of state to the next stage of modeling of heavy ion collisions, which is with a hadronic transport approach. And one popular one in the field is known as SMASH. So we decided to utilize the hadronic list from SMASH in order to achieve consistency across the modeling of these heavy ion collision systems throughout the different stages. So also in this case, the equation of state is built from the Taylor expansion of the pressure. So we utilize again the Taylor expansion coefficients that have been calculated on the lattice. So in these two plots, I'm comparing the different conditions again between vanishing chemical potentials and the strangeness neutrality conditions for the second order Taylor coefficient as well as the fourth order. And what these plots show is that they're qualitatively similar, but of course have different quantitative features. So they approach different limits and high temperature. And in addition, what we can see in the fourth order moment is that the broadness of the peak in the vanishing chemical potential case is much larger than for the strangeness neutral case. So going forward after this comparison, I'll only be using the strangeness neutral case, which are these points here in red. So if one was interested in that, you could recreate the phase diagram from the lattice, similar to the one which I showed for the four-dimensional equation of state in the phase diagram. But in this approach, we actually want to go beyond the first principles information in order to implement critical features in the phase diagram and study the effect of a critical point on those observables. So the criticality is actually implemented by relying on the principle of universality classes. So the critical point for QCD has been shown to be in the same universality class as the 3D Ising model. So this was a natural choice for our critical point in the phase diagram and implementation of that into our model. So the phase diagram for the Ising model is actually shown over here in this plot on the right. And this is actually analogous to the QCD phase diagram when we consider that the magnetic field here in this Ising magnetic system is an analog to the baryon chemical potential, and the magnetization, the order parameter for the Ising model is analogous to the baryon density. So in our approach, we actually utilized not the temperature, but the reduced temperature. So this reduced temperature will shift down the critical point to the origin of the Ising model phase diagram. So in addition, the pressure that allows us to build out the equation of state comes from recalling that the pressure and the Gibbs free energy are related up to a minus sign. One thing that we know that is different between the Ising model and QCD is that we know that the critical point doesn't just sit along one of the axes. So it doesn't sit along the t-axis in the QCD phase diagram, but it's at some point along the chiral phase transition line in the QCD phase diagram. So somewhere in the TMUB plane. So we need a mapping that will allow us to place this critical point in a location that's relevant for QCD. So the mapping that we utilized is shown over here in the equations on the right. So this is a linear mapping to paste the Ising model phase diagram or the Ising model axes onto the ones for QCD. So this allows us to choose the location of the critical point, so this TC and UBC, as well as the angles of the axes between the two Ising model axes. And there are also two scaling parameters, which are omega and rho shown here, that actually determine the size of the critical region in the phase diagram. So all in all, we have 6 non-universal free parameters. So there's no universality arguments that allow us to determine where this critical point should be placed in the phase diagram. So this is something that the user of this code can actually choose. And in the program itself, we offer several different options. So one can place it freely in the phase diagram and you have 6 free parameters, but another choice is to utilize the fact that you know the critical point is going to lie somewhere along the chiral phase transition line, for which the curvature parameters have been calculated from Lattice QCD. So by utilizing this chiral phase transition line, you can eliminate 2 of the 6 free parameters. So once you choose a mu b that your critical point will have, by default, you have as well the t, and you also know the angle of the this angle alpha 1 of the t-axis with the mu b axis in the QCD phase diagram based on the curvature parameter from Lattice QCD. So, okay, this mapping tells us how to stick the Ising phase diagram onto the one for QCD, but how are the critical features actually implemented with our approach? So for this, we utilize the scaling equation of state. So the parametric representation of the 3D Ising model is given via the parameters r and theta. So this scaling equation of state encodes the critical features into the QCD phase diagram with the correct, with the correct parametrization of the critical features. So this goes back to one of the original formulations by Isentropic, which gives us a convenient parametrization for these critical features. So the magnetic field H, along with the reduced temperature T, the magnetization, and the Gibbs free energy are all given as functions of these parameters r and theta, where actually the singularity itself is contained entirely in the r parameter that scales with the critical exponents. So these critical exponents are alpha, beta, and delta as given in these equations here, and they're derived from some renormalization group approaches, as well as what's been given by Isentropic. So that's where these critical exponents come from. So the free energy that I'm giving here thus describes the free energy of the singular part. So this is the free energy that describes the critical point features. But in general, one could also have a free energy that includes a background portion. You're free to add something that does not have a singular contribution to get your overall pressure in the equation of state. So one choice that we made is given here in the first equation on this slide, where we utilize a background free energy such that overall our pressure reproduces the known results from Lattice QCD. So our background free energy doesn't exhibit any singular behavior, and by this we ensure that we reproduce the first principles equation of state in the realm that it's available. So in other words, the non-Ising or our background part is simply the difference between the lattice and the Ising quantities. So this can actually be seen in each of the plots that I'm showing here for the Taylor expansion coefficients, where the lattice contribution along with the Ising model contribution, their difference gives rise to this non-Ising contribution shown in blue for each of these quantities. So furthermore, we also know that the overall pressure in the phase diagram has to be matter-antimatter symmetric, since we know that QCD is also symmetric about the mu b equals 0 axis. So when we do our full reconstruction of the pressure, we utilize the Taylor expansion of the non-Ising parts, as well as the full symmetric Ising model pressure. And this symmetrized pressure is just determined by utilizing the information at negative chemical potentials in order to have the appropriately symmetrized pressure for the Ising model. So the final output of our equation of state is shown here for different quantities that make up the equation of state. So it's the reconstructed pressure shown here along with its first chemical potential derivative, the baryon density, and the energy density as well. So what you can see is at the level of the pressure, there's maybe, you can't see it on your screen, but a slight kink here at values of the baryonic chemical potential larger than the critical one. But further derivatives actually help to reveal those critical features, and we can see the jump in the baryon density as well as the energy density at larger values for the chemical potential. So in addition, we also calculate the entropy and the speed of sound. So the entropy also shows this, this jump, but the speed of sound is shown to dip to 0 at the critical point itself. So there are still two free parameters in our model, which is the omega and rho that I introduced before. And these also can be used these free parameters can be constrained in our equation of state by comparing to the forthcoming beam energy scan data. So I'm just showing how the parameter the parameter omega actually changes the effect and the size of the critical point for these different values here. So in the plots that I've shown earlier, this is the same value, taking omega equal to 2. And then if we decrease omega, we increase the size of the critical point contribution in the phase diagram. And by taking a larger value of omega, we can actually shrink this effect. So once the data becomes available from the experiment, we'll be able to constrain these parameters and actually determine what the size of the critical region is in the phase diagram based on the values of these parameters. So furthermore, also showing what the trajectories through the phase diagram are for our heavy ion collision system for our equation of state, we look again at the isentropes, so fixed value of entropy of a baryon-number. And what we can see is along this chiral phase transition line, the effects of the critical point start to become manifest as we approach the critical point itself. So in addition, we can compare the two different cases on our conserved charge chemical potentials, namely whether it's the strangeness neutral case or the vanishing chemical potentials. And again, we can see a vast difference in the initial conditions. So these are shifted to much larger values of mu b for the same, in the case of vanishing chemical potentials, there's a much larger temperature for the same value of the chemical potential. And in addition, if we look at different curves through the phase diagram, we can also see that, again, we're strongly affected by the presence of the critical point, since we know that both the entropy and the baryon density have just this discontinuity in the phase diagram, as I showed before, for the five different observables from our equation of state. So one further quantity that we also wanted to provide with our equation of state that's important for the hydrodynamic modeling of heavy ion collisions is the correlation length. So this is the way that the correlation length can be calculated within the 3D Ising model. And at this stage, our equation of state only puts out this critical contribution to the correlation length, since as far as we know, there's no calculations yet of the correlation length from Lattice QCD. So the critical correlation length itself is shown over here in the full phase diagram. So it's quite smooth everywhere, but diverges at the critical point itself, which is the expected scaling behavior for this quantity. Okay, so I see that I'm a bit early, but hopefully that leaves plenty of time for questions. So I'll just quickly wrap up to say that it's important to utilize constraints on the conserved charges when you want to compare to heavy ion collision data, when in that case, you have the strangeness neutrality conditions on the conserved charges. So in addition, there's this new equation of state that contains a critical point that not only implements these conditions of strangeness neutrality, but also has the same hadronic states from the SMASH hadronic transport code, such that the full evolution of the heavy ion collision system can be modeled and everything is consistent within that modeling. So in our equation of state, we have seen the expected critical features, and we see that especially the isentropic trajectories give rise to different initial conditions, which is important for heavy ion collision phenomenology. And we also provide a calculation of the correlation length in the 3D Ising model. So thank you for your attention. I'm happy to take any questions and turn it over to Christian.
Thanks so much, Jamie. That was a great talk, and your timing is perfect. So let's get started with the Q&A session. Please just raise your hand, and I'll take care of the rest. So the first one is Dean Lee.
Hey, Jamie, that was a great talk. Very clear and very nice, impressive results. I did have a question. So for your best estimation of the critical point, the critical endpoint, what is the baryon density at that point approximately?
Okay, so that's an important question, because what I'm showing here in this equation of state is not an estimation of the location of the critical point. It's just utilizing this mapping in order to place the critical point in a regime of chemical potential that can actually be reached by the beam energy scan collisions. So this is not a prediction for the critical point by any means. This is just in order for the hydrodynamic simulations to have some effect of a critical point implemented into their necessary input, which is the equation of state, and actually see what the observables look like. But there are other models. I have a colleague at Houston who is working with a holographic equation of state from black holes. And I believe his prediction, now in terms of density, I'll have to try to do that conversion in my head, but I think that his prediction for the critical point is something like 720 in mu B, and the temperature is around 70 MeV. So if we're trying to go into density, that might be roughly 0.7, 0.8 saturation density.
Okay.
But I'm not very I work in mu B, so maybe don't trust everything to my conversions in terms of the densities. But I am aware of those calculations, and they seem to be pretty robust from these universal properties of the holography.
Great, thank you.
Thanks, Dean. So the next one is Pavel.
So in your considerations, you have carried out static considerations, but the transition to the phase transition is dynamic. You get in and you get out. What if you overshoot that region, rapid changes in thermodynamic properties? You can get in and you can get out, never knowing that they were there.
So this, as you said, is just a static picture. So we feed this into the hydrodynamic simulations, which then can treat the system. So I think the way I would try to answer this is, so our computational grid is in a step of 1 MeV. So we go a step of 1 MeV in temperature and a step of 1 MeV in UV. And if there's something in between those step sizes of 1 MeV, we might miss something. But I think in general, since our grid is pretty fine, we should be able to implement those features.
Yeah, I understand that, but the issue is nature. If the nature goes in and it goes out of the region without noticing that, if you waited very long time, you'd have changes.
Okay, so your question is about finite time effects or finite size effects.
Yes, about time it takes to equilibrate with change, with significantly changed thermodynamic properties.
Right. So this is all the precursor to something that allows you to simulate this strongly interacting matter. So at some stage in the simulations, one could try to address these finite time effects. But at this stage, this is just kind of the input for those.
So just to jump to quick expectations. So basically you would expect a strong increase in entropy production.
Oh, sure.
That would be the observable. Yeah, okay.
Yes.
Thanks.
Thank you.
Thanks, Pavel. Any further questions? Oh yes, Scott Vogner. No, Scott Pratt, sorry.
Okay. Yeah, hi, Jamie. So can you produce tables in, because if I'm going to run a hydro calculation, I need an equation of state in terms of density and energy density, not mu and T. And so do you produce those tables?
So what we can do as far as the way that the code runs now, we can create tables where basically you have, in your table, the NB here and the epsilon here. But that being said, there's no treatment of the coexistence region if you do that. Right?
That was the next question.
Right. There's no way for us to be able to model the multiple solutions that you get in that regime of the first order phase transition, when we would just simply paste together the columns of the baryon density and the energy density. So in principle, as long as you're in the crossover regime, we can prepare such a table, but once we get into the coexistence region, we don't have the full solutions. We only have one of the three possible
it's really
solutions.
tough for hydrodynamics, because if you're running a simulation, you don't have some trajectory that's aligned through the phase diagram. It's a big swath, any collision. And there's no way to hit the critical point without also going south of the critical point.
Right.
I mean, it's just obviously impossible. So
so the best,
not useful until you've got the whole thing.
The best that's in the published version is a Maxwell construction. So there's some ability to do a Maxwell construction, but actually I'm working on a description of the coexistence region with Volker Koch at this stage.
Okay.
So we're trying to implement this, and hopefully we'll have some updates relatively shortly.
Okay. Then another question. So the lattice results, these expansions in mu only go down to temperature of about 135.
Oh, right.
And shortly above that temperature, the degrees of freedom become sort of ambiguous. You're in the crossover region where neither hadrons or free quarks are probably really the right, clear degrees of freedom anymore. But maybe there's a little window, around 138 MeV or 140 or something, where you might think it's still hadrons, but lattice still works. And so do those coefficients for mu squared mu to the fourth fit the lattice results in that little bitty window?
Yeah, so that's exactly spot on. So some of the lattice results go down to 130 and some stop at 135. But in general, we calculate the Hadron resonance gas model up to, I don't know, let's say 150 is a reasonable cutoff. And then we find the overlap regime and we give the same cutoff temperature for the HRD for all our observables, which was 135 in this case.
So there's absolutely no unusual behavior below 150 MeV in
That's right.
In any of the fluctuations.
That's right.
So it's very hard to say that the lattice is giving you some evidence of anything below 150 MeV.
Yeah, since it matches so well with the HRG model, we say that it's one possible conclusion is that it's in the hadronic phase of this regime.
Oh, okay.
But yeah, they match very well for all of the susceptibilities up to order MeV4.
Okay, but aren't there calculations all the way to mu be 8? And,
for the various,
but
for
not to
all,
that low temperature or what? Okay.
yeah. So for all possible susceptibilities up to order 8, no, but some are available. I think chi 2b, there's a preliminary result for this up to order, sorry, chi 8b. Chi 6b is available, as well as some results at order 6, but order 8 is still,
Okay,
I think,
no, but the
under
order
calculation.
6, now do the order in 6 and 8 match the Hadron gas too? The ones
Yes,
that
indeed they do.
Okay.
In this regime of about 130, 135.
Yeah, this little window you got there.
Yeah,
Okay.
exactly.
Thanks.
Thank you.
Thanks, Scott. Dean?
Yeah, so Jimmy, as Scott was asking these questions, I was wondering to what extent, so we do some calculations of symmetric nuclear matter from the hadronic, the nucleonic point of view. So we could go up to densities about to saturation densities, and probably up to temperatures of about 50 MeV. There be an overlap region where we could try to match with what your equation of state is saying?
That is an excellent question. 50 MeV. This is then still in the hadronic phase, but that would be interesting, especially at the high densities, because so there are different versions of the Hadron resonance gas model. You can go beyond the ideal gas formulation and start to look at, the van der Waals equation of state, which describes the nuclear liquid gas phase transition. But there's not yet a consensus on at which stage you should switch to the van der Waals equation of state, or if you should use the van der Waals equation of state all the way down to 0 temperature and 0 μb. So I think this could be indeed something that we're interested in, because we're trying to build out the equation of state into the neutron star regime. So we want more information at higher densities. So I think this is something that we're currently working on with a few new endeavors within some new collaborations that my advisor is involved in, like the Muses collaboration and the NP3M collaboration. So yeah, I think we would be very interested in comparing our results in those regimes.
Okay, great, thanks.
So Jamie, I was going to ask the same question, so let me extend on this a little bit. So, but I think you've partly answered it already. So at 0 temperature, there are also very promising QCD-based results at 3 times saturation density and higher from the functional renormalization group. Would that help at this stage?
So 3 times saturation density
at 0 temperature in symmetric nuclear matter.
Yeah, this is quite far in terms of μb, if I have the conversion in my head right. But nonetheless, if we want to know, so okay, at 0 temperature, it's kind of hard. So the equation of state that I'm showing here goes down to about 30 MeV in temperature. But in order for it to be used in hydrodynamic simulations, it needs to go all the way down to 1 MeV, basically, almost 0 temperature. So any constraint at that level is something I think that would be useful for us. But in this high density regime, I'm not sure we can push the lattice thermodynamics that far at this stage. But again, any constraints that we can get to help our equation of state in areas where we don't know is very wanted, very much wanted.
Yeah, so let's discuss this in more detail offline. I've got a couple of questions along those lines.
Okay, perfect.
Just a final one, perhaps slightly more technical. I think it's somewhere in slide 12. You showed this Padea approximant.
So I was on slide 12 there, but it was back. I'm sorry. 1 second. This one. Yeah.
Yeah. So how do you deal with those poles? And in particular, if I remember correctly, you replaced the first equation by the second, which is just the hyperbolic tangent, right?
So this particular fit function that we utilize is just one that gave us the smoothest approach across, 800 MeV in temperature. So we don't need to take any derivatives or anything like that. So we don't have to deal with any effects of the denominator popping up in our case. So we just parameterize these curves, and then from each susceptibility and its smooth parameterization, we reconstruct the Taylor expansion of the pressure.
So what I mean is, the A has poles, right? And it could be in the domain you are interested in, but you're saying that that's not a problem, right? For you, it's just the model that fits best in,
Right.
in whatever measure
Exactly.
the data. Okay.
Right. That's right. Yeah. Thanks for the question.
Okay. So any more questions? No. Okay. Thanks again, Jamie. That was a nice and great talk and Q&A session. So two announcements. The first one is Jamie's here. So please feel free to stop by at her office, which is Aaron's office as well, today and tomorrow. Is that right, Jamie?
Yes, technically I'll be here through the holiday as well, but I don't think anyone else will. So
yeah,
I don't think I'll be coming
forget
up
about
to the
this.
facility.
Okay, so today and tomorrow. And the
Yeah.
second announcement is, so I'm not one of the organizers, but nevertheless, I would like to advertise the information and statistics and nuclear experiment and theory, in short, ISNET meeting that is going to be hosted by MSU and EFRIB in December 13th through 16th. So this is a nice place and environment to learn about Bayesian methods and statistics in general. So please mark this in your calendar, and there might be a joint nuclear theory seminar with the ISNET meeting. So with that, I would like to wish you all a happy Thanksgiving, and see you around.
Bye. Thank you.